Lucky here. I hope by now you're convinced these things are pretty cool. But what are they? Some kind of glow-in-the-dark dartboard? A bioluminescent donut, perhaps? Believe it or not, these are actually rocket engines. Well, sort of. More accurately, these are all examples of electric space thrusters, which are really more like a particle accelerator that can be strapped to a satellite instead of using a chemical rocket engine. I've been fascinated by these exotic beasts ever since I learned you could use them in KSP to ping-pong around the solar system, or just hack their thrust and break the game entirely. But what does a real electric thruster do, and why are they replacing conventional rocket engines on some spacecraft? A thruster is a device that can push a spacecraft around. Whether you want to fly to Mars, eject from the solar system, or even just maintain a satellite in orbit, each mission requires a certain amount of change in velocity, or delta V, to complete its goals. Newton's third law states that in order to change your velocity, you need to push something in the opposite direction. Since there's nothing to push off of in space, we have to bring it with us in the form of propellant, which is just a fancy name for rocket fuel. Now we want our propulsion system to be as light as possible so we can maximize our payload, meaning we want a thruster that can provide our delta V using as little mass of propellant as possible. According to conservation of momentum, if we want to use less mass to get the same delta V, we need to fire it backwards as fast as possible. One of the easiest ways to expel propellant backwards is to have a bottle of compressed gas that gets opened. Adding a nozzle to this helps direct the exhaust molecules to all go in roughly the same direction. Chemical rocket engines improve on this by first burning the propellant, which heats up the exhaust before it flows through the nozzle. This means the molecules in the hot exhaust are bouncing around faster, and once the nozzle gets them moving in the same direction, they'll be moving faster. Unfortunately, there's a hard limit to how fast we can accelerate the exhaust with this technique. There's only so much chemical energy in the propellant, and we need to turn that into kinetic energy to accelerate the exhaust. Even if we had a perfect rocket engine, every kilogram of exhaust couldn't be accelerated past the velocity where its kinetic energy would outweigh the chemical energy it started out with before it was burned. This limit can be slightly expanded by using a propellant that has more chemical energy to begin with, but these propellants are often some of the most dangerous chemicals in existence and have their own set of handling problems. On top of this, we have to deal with problems like not melting our rocket engine and losses due to entropy generation.
In this house, we obey the laws of thermodynamics!
Even with all our modern innovations, rocket engines still have roughly the same exhaust velocities as they did 50 years ago. Wouldn't it be easier if we just skipped the hot gas portion of our thruster entirely and injected kinetic energy directly into our exhaust? Good news! This is exactly what particle accelerators do. Yep, the same machines that smash atoms and accelerate electrons to nearly the speed of light can be used as a spacecraft thruster. The simplest form of particle accelerator is called an electrostatic particle accelerator. It consists of two plates with a high voltage potential between them. If we introduce a charged particle between them, say a positive ion, the ion will be accelerated away from the positive plate and towards the negative plate. If we drill a bunch of holes in the negative plate, the ion will most likely pass through the holes and be ejected off into space. This method can accelerate our exhaust insanely fast. For example, if we use xenon ions as our propellant and charge our plates to a voltage of 10,000 volts, or roughly the voltage of a static shock, then we could accelerate our exhaust to over 100 kilometers per second, or in imperial units, really fast. This is essentially how gridded ion thrusters work. First, we create some ions in an ionization chamber by bombarding a gaseous propellant with electrons. Then, we accelerate the ions towards a negatively charged electrode screen. Finally, we fire some negatively charged electrons into the exhaust plume. We need the electrons to neutralize the plume because otherwise our spacecraft would quickly become negatively charged, and the ions in the exhaust would come right back to our spacecraft. This would not only produce no thrust, but it would also be like sticking our spacecraft into the plume of a rocket engine, slowly eroding it. Ion thrusters are great because they are relatively simple devices and very energy efficient, leading them to be used on many deep space missions like NASA's Dawn mission to orbit Ceres and Vesta, or JAXA's Hayabusa missions to sample asteroids Itokawa and Ryugu. Unfortunately, ion thrusters suffer from one major drawback: thrust. Thrust is the amount of force our thruster provides, and is typically around the weight of a few paper clips for a gridded ion thruster. This means it could take months of thrusting to complete a maneuver, limiting our use case to orbital corrections and deep space maneuvers, where we would be coasting along for months anyways. There are a few reasons for this limitation. First, it takes a lot of electrical power to accelerate even a small flow of ions to such a high velocity. In the future, we may be able to get around this by using beefier power supplies like a nuclear reactor. But the second reason is more fundamental. If we try to push more ions through our thruster per second to create more thrust, eventually there will be so many positively charged ions in the thruster at any time that they would repel any new ions trying to enter the acceleration region. We could try making our thruster bigger so that there's more area to spread the ions over, but that makes our thruster heavier, and maybe even too big to fit on the spacecraft. We could also try increasing the acceleration voltage to get the ions out of the way faster, but this makes our power supply heavier and would eventually cause arcing between the electrodes. If we want higher thrust for our mission, we need to entirely rethink how we're accelerating the ions. Enter the Hall effect thruster. The idea behind these mysterious beasts is to inject negatively charged electrons into the acceleration region to cancel out the charge of the ions. That way, we can inject as many ions as we want without them being repelled. But wait, if electrons are many times lighter than ions, won't they get pulled out of the acceleration region even faster than the ions? That would be true, if not for the power of magnets. We can apply a magnetic field to the acceleration region, which some nincompoop decided should be represented with the letter B, for magnetic field. Anyway, the magnetic field will apply a turning force to the electrons, causing them to follow a loop-de-loop pattern around the thruster, instead of going straight to the positive electrode. Ions also feel this force, but since they are so much more massive, they hardly get deflected at all before they leave the acceleration region. Here's what this looks like in a cross-section of a more realistic Hall thruster. We can use solenoid coils to create a magnetic field near the exit of the thruster. These trapped electrons also help concentrate the electric field in this region, so we can get rid of the negative electrode grid as well. Eventually, the trapped electrons will collide with enough atoms and ions to slowly make it to the positive electrode, which has the added benefit of knocking off electrons from some of the atoms they collide with, creating the ions we want to accelerate in the first place. To summarize, a Hall effect thruster works by injecting gas near a positively charged electrode. Collisions with electrons turn these atoms into positively charged ions, which are accelerated away from the positive electrode at huge velocities. Meanwhile, some of the electrons from the neutralizer are getting trapped by the magnetic field in the acceleration zone, keeping it neutralized. The rest of the electrons are getting pulled into the exhaust plume, keeping it neutral so it doesn't make its way back to the spacecraft. These are just two ways electrical energy can be used to power a space thruster. Other ways, such as pulsed plasma railguns, microwave-powered thrusters, and even nuclear fusion-powered thrusters have been proposed, all with varying degrees of development and success. I personally think these thrusters will play a central role in our future in space, making us more connected on Earth and letting us explore the reaches of our solar system and beyond. I hope you enjoyed this video and learned a thing or two about how these space-based particle accelerators can be used as rocket thrusters. Like and subscribe if you'd like to see more videos on the physics of how these electric space thrusters work and other engineering topics.